For this example, I think it's labeled as example either 3 or 4 in our course notes. What we're going to do is we're going to step it up from example 0 and 1. We're going to look at multiple stories and where not all the stories match. And by that I mean that the number of bays in each story doesn't carry all the way through. Again, it's arguable whether or not the portal frame method, the approximate method of portal frames, is applicable to this, but the idea for us is mostly that we learn how to use it. So what we have here is a 3-story structure. The first story, the bottom story, has 3 bays, one measuring 25, 30, and 25. I think it's feet or meters, it doesn't matter. The top 2 stories, the second and the third one, are only 1 bay wide. There are lateral forces of 3, 10, 5. Again, kips or kilonewtons, doesn't matter. The height of the stories vary. They're 15, 12, and 12. And with this question as well, the ultimate goal is to come up with the reactions at these fixed supports, and then the maximum shear, axial forces, and bending moments inside the structure. If you're wondering then how this method works in general terms, maybe start with example 0 or example 1, which are linked for you at the bottom in the description of this video. We're going to start off first with our first step, which is to locate all the inflection points. And the way we do that is based on the 3 assumptions that we're making for this method, the portal frame method. If you can't remember what these are, please review the video that I've linked for you in the description about the assumptions, the portal frame assumptions we're making for inflection points. We're going to go with assumption number 1, which tells us that inflection points are located at all mid-spans for all members. So for us, for every column and every beam, I'm going to go midway and insert an inflection point. If you're writing this out in pencil or paper, pencil if it's for a test, pencil or pen, pencil if it's for a test, I don't need you to erase the space and put an inflection point there, just mark it, okay, on top of the line. So this is now done. We have inflection points everywhere. I'm also going to label the inflection point because it makes it easier to analyze. Okay, 1 through 13. Step 2 is figuring out the column shears. I think I misspelled columns, shears. Another way to call this is to figure out the inter-story shear. That is the shear in the columns that separate one story from the next. Right? So we're looking for the shears right here in these columns. Again, if this method is not looking familiar, try out first example 0 or example 1. So the whole point of this is that we're able to cut, kind of like as if it were a tree, at every story, top to bottom, we can cut through the inflection points for every column. And we have to remember that when we do that, the shears in those columns must equal to all the external forces above. And then, that the shear in the outside columns are the same, the shear in the inside columns are the same, and the shear in the inside columns are twice the outside columns. So what we're going to do, first of all, is start top to bottom. This is critical. Well, I would say at the very least it's the right way to start if you're not familiar with the method and you're still learning how to use it. So I'm going to start with the top story. I'm going to cut through 5 and 11. Okay? So it's going to look like this. obviously not to scale. So I've cut through 5, I've cut through 11 right there, and I have interior shears. And they must be going that way because the only applied force in this case is 5 going this way. And then what I'm also told is that the shear in the outside columns must be the same. There are no interior columns here, just outside ones. So we know that they have to be the same, like this. Right? Column V for shear. So if we know that these shears are the same, and the only applied force is 5, are we able to figure out what the value of V is? Certainly. We don't even have to write out the equation of equilibrium in the x direction, but we can if we want to. I'll be thorough and write it out. But it's okay if you just write the answer. So in this case, we get from sum of the forces in the x direction, okay, 5 is equal to 2v, which means that in this case, v is equal to 2.5. And again, you put the units there of the force, whether kip or kilonewtons. Okay? So what we have already is 5x and 11x, and I'm going to make a note of them right here. And they're both equal to 2.5, like this. Now, if you're not sure why I'm showing this in this direction, check out example 0 and example 1. Great. There are no interior columns here, so I'm ready to move on to the next story below. For the next story below, I'm going to go through 4 and 10, okay, top to bottom. So I'm going to do that work over here. So I'm going to say next. And I'm cutting right there through 4 and 10, halfway up. Here there's an applied force of 5. Here there's an applied force of 10. And our assumptions tell us that the shear in these columns and all of these columns together must equal that. Also, the shear in the outside columns must be the same. We have no interior columns in here. And again, I'm just going to call them V for shear, but you can call them whatever you want if it helps. Okay. If we know that there's an applied force of 15 in the horizontal direction, and each one of these is V, can we figure out how much each one of them is? For sure. We'll do this exactly the same way. You know how to do it, I do too. So I'm simply going to write that V equals to 7.5. I'm okay if you write out the full solution too. I'm okay with that. So now that we know that that's 7.5, I'm going to remind myself that 4x and 10x are 7.5. And the shear is in this direction. Finally, I'm going to cut through right here, the final story. Now, I'd just keep doing this if this were even 100 stories high from top to bottom. The bottom story, look at this, is different from the top two, right? This has 3 bays. So let's see what that does. Finally, So here I cut at the inflection points at 1, 3, 9, 13. Each one of these has a shear, right? An interstory shear. They go this way. Like that. And what we know, remember from our assumptions, is that the outside columns are the same, right? They have a shear of V and V. And the inside columns have a shear that's twice the outside columns. So in this case, we have two inside columns. Each one is twice the outside column. Okay? So V and 2V. If we had 100 inside columns, each one would be 2V, 2V, 100 times. Okay? Great. Can you see where we're going next with this? Yes. We're going to compare or balance out the horizontal forces applied, the exterior horizontal forces, and the interior shear forces. And that will help us figure out what V is in this case. Okay? I'm going to be thorough and I'm going to write it all out. Sum of the forces in the x direction equals to 0. In this direction, we have 3 plus 10 plus 5. That's 18. In the opposite direction, we have V plus 2V, that's 3, plus 2V, that's 5, plus V, that's 6V. Okay? And they're negative because they're going in the opposite direction. A common mistake here, especially when one is rushing, is to simply write that number correctly minus 4V, right? Not recognizing that each one of these is 2. And that's true especially when you have a whole bunch of interior columns. Each one interior column is 2V. So let's check this out. V equals 2, 3 kilonewtons or kips, depending on the units of force that you use. So now that we have V, we also have 2V. And I recommend always make the point of writing it out. That way you minimize the chances of a mistake. 2V is 6. I'm going to remind myself what they are by putting them here. 1x and 13x, they're V, right? So they're 3. And 3x and 9x, they're the 2V. So that's 6. So that's 3. Terrific. Now that we're at this point, we're ready to move on to step 3. Remember what that was? Isolate joints. So that is where we go, and we basically do our equations of equilibrium, our 3 equations of equilibrium at every joint. We scoop out every joint between the closest inflection points. So for G, we scoop out G between 5 and 8. Okay? So I'll let you figure this out. You simply use the same method that's shown for example 0 and example 1. I have posted for you the answer to this. That is the final answer with the axial shear forces reactions and the bending moment diagram, and the bending moment interior reactions and exterior reactions. Okay? So give it a try. This will feel tedious and long at first, but once you get it done, you'll know you can do it. Okay? I think I'm going to pause right here. Before I do that, though, I want to point out a few things. Okay? The most common mistake in this step for multi-story buildings, especially when you're new at this, is the following. Forgetting about these exterior forces. And what I mean by that, when you go to do E, and you scoop out E between 5, 7, and 4, it is common, especially if you're new at this, to forget to add 10. And if you forget about that, your answer is incorrect, right? It's a big boo-boo. Ditto here for this location here. This is B. When you scoop out B between 1 and 2, forgetting to put 3 is very common. It's a common mistake. So make sure you don't make those mistakes. Which brings me to, if your answer is different from what I posted, there's a good chance this is the first thing you should check. The second one is to see if these interstory shears are correct. Typically, this is where the common mistake happens in forgetting that these are 2V. All interior columns are 2V. Okay? Thank you for your time, and good luck.